Thanks for watching this presentation, and don't forget to like this video. Please leave your comments and subscribe to the channel for previous videos and more videos coming to our RailFan playlist.
Nice here. I want to thank Bruce Bracken for helping me with that. Our system computers on our railroad are very locked down, so it's very difficult for me to share files and everything like that in a conventional sense. So that's why it always takes just a few minutes. For those of you who are wondering, how many times can you talk about rebuilding a big boy? You can talk about it a lot. I got thousands and thousands of pictures, but I wanted to focus mainly on the boilers. You know, the machinery and the mechanical stuff and all the neat stuff that we do to run the steam locomotive and to plan is always really fun. It's interesting, and it's one of the more interesting and enjoyable aspects of my job. But it's the boiler that is really, I think, the magical part of the story. So we started, gosh, it's 14 years ago. It's hard to believe time flies so quickly. But in 2011, we started looking at all kinds of different things that we needed to do. 3985 needed some really significant mechanical work. So did the 844. And so that positioned us to start gearing up. And it's a plan as you go, fix as you go mentality, but in my view, I wanted to make everything as new as we could. And I had a very unique opportunity that our executives were solidly behind me in that effort. We had conversations about the mechanical condition of the locomotives and when they were last thoroughly rebuilt. And if you think about when steam locomotives were thoroughly shopped, that's back when they were running them. And a locomotive, most of them were scrapped, and for a variety of reasons, locomotives didn't get scrapped, they got preserved. Well, not necessarily preserved for any reason other than they just happened to be preserved. So they had varying mechanical conditions on the locomotive. And that was the backdrop in which I got started, having those very thorough conversations about what to do. People to hire, parts to acquire, fabricate, design, a shop that needed to be fixed, you know, and you just chip away at it. You start putting together a 1-year plan, 5-year plan, and beyond that. So I have so many different photographs, and it's one of the more challenging things for me to do is to put together a presentation that A, isn't going to bore people who aren't really into the nuts and bolts side of it, and then kind of go through and make sense of the complexity of what you're about to see. For those that are familiar with steam locomotives, maybe some of this combination of metal that will look familiar to you. So that will be my job, is to help you understand what it is. I'm enthusiastic about it because I was there, I lived through it. These are all my pictures. And there was a reason I wanted to capture these images for posterity, but also because of the history that we were making. In museums and places that restore aircrafts and old automobiles and old ships, you know, it's common that you take something apart and you completely rebuild it again. But to have an opportunity with a big giant locomotive, I will never forget that day when I told the senior vice president, I want to do it right. I want to make a lot of new parts. And I got this nice grin and this nice emphatic gesture. Yeah, that's right. So it was with that we got started on doing all these things. Sometimes it wasn't always pleasant when you report to the headquarters that something needs to be rebuilt. When it was planned that it didn't need to be rebuilt. That's a difficult sell. And then going forward, when you rebuild whatever it is you're talking about, what is the plan to maintain it? And what is that going to look like? What is it going to cost? And that was the commitment that I was making, that the locomotive would be so thoroughly rebuilt and restored and operationally sound, they would have many decades of good serviceability. And the mileage that we put on the equipment is nothing, not even remotely close what the railroad put down on them, even in 1 month. For example, on the cab forwards on the Southern Pacific, those big monsters, which weren't really that much smaller than a big boy, those big 2884s, or correctly, it's a 4882 cab forward, they would run about 7,000 miles in a month before the wheels needed to be turned, before certain machinery components needed to be renewed. And the 4,000 class, the 3900s, the 800s, all the steam locomotives are nothing like a locomotive today. How many people go out and watch trains go by? We got a lot of rail fans, that's good, lots of you. So you know what it's like when you're standing. Picture yourself up at, let's just pick a location on the Union Pacific, 3-track. They built 3-track specifically for steam locomotives. They were after one goal, and that goal was to make the steam locomotives more efficient and to allow them to pull more, to save money, to save crews. Sounds familiar. Save money, save crews, save resources. Nothing different today. When you go watch a train go by, we have a train at NPFR, the NPWC, West Colton, Fresno. Those trains were enormous. It makes the designers of the big boys and the planners back in the 1940s, they would be smiling. They would be amazed to see what we're doing today, because we're doing it with the technology that we have. They were doing it with the technology that they had back then. So a 4000 was rated for 6,000 tons up 3-track. 6,000 tons, that's about 3 times less than that FR train I was telling you about. So I was up the other day and we took a test run. One of the gentlemen that works for me is getting his engineer's license, so we took a run. I put him on a grain train and I picked him up at Medicine Bow. And we watched that big train go by. 24,000 tons, 16,000 feet long. Think about that. You've got a General Electric locomotive and an EMD locomotive. Forgive me. I need to take this real quick. Give me just a quick moment. So back to my story about the fabulous locomotives that they have today and the locomotives that they had in years past. So you got these big, massive locomotives designed to produce power. The locomotives we have today run for thousands and thousands of miles. You check the oil in them, you check the water in them, they're all GPS, they're linked. Every parameter on that locomotive is being monitored. If there's a problem with it, there's a lot of what we call help desks, people there who are linked into it that are figuring out and troubleshooting. Kind of like the old days. They just did it with a telegraph key. Later on, they did it with a telephone. So it's neat to see how the railroad's evolving. So with that backdrop, I have, pardon me, an update coming in here. I guess it's the door. She can't get in the door of the building.
Can you run back and go down by the elevator for somebody?
Okay. Whew. Well, that makes me feel a little more comfortable. Okay. So it's with that as a backdrop that I wanted to undertake the level of work and wanted to gather a group of people that would help me. And that's exactly what we did. So I was not able to get all these photographs, and we've got to solve that problem. It's a problem for me to solve, but I have so many of these cool pictures. So we're going to scroll through what Bruce, I've been able to give Bruce several of these presentations. And so, well, let me see if we have some of the boiler stuff.
What are these parts?
Well, this is a suspension system. He just kind of opened the presentation and it just kind of opened these. So what these are brand new castings of a suspension system. So how many people like Moffett Malleys? If you look at a picture of a Moffett Malley, you're going to see this. That's called an equalizer over a driver. It's a unique part of the suspension system that allows the suspension system to be fit within the frame versus over the wheel like in a conventional locomotive. Well, those parts are completely worn out, the original versions. Like so many pieces of the locomotive, you've got a machine with 1 million miles on it, and it's been ridden hard and put away wet. Just like today. You go up, watch the trains go on 3-track, and you watch a business that buys machinery. And that machinery is not like your automobile, where you drive your car If you drove your car like we run our locomotives, your car would last 10 minutes. I mean, these locomotives are nothing like what we're accustomed to seeing. Which begs the question, well, why can't we make a car that runs more like a locomotive? But that's a whole other topic. There's a roller bearing in part of the suspension system called an eccentric rod. This controls the valve. This is the eccentric crank, which is brand new as well. So we take all of this equipment apart. The heart of the locomotive, of course, is the boiler. And that's usually the piece that is seen to be the most complex because of what it does. The boiler is what generates the power of the locomotive. That's where the steam, the water is boiled and generated into high pressure steam. We're not talking high pressure like a power plant or high pressure like a nuclear submarine or an aircraft carrier. It's not that high pressure. In a steam locomotive world, high pressure is 300 psi. High pressure on a big nuclear submarine is something completely different. But for 1940s, these boilers were very well designed. As an example, the boilers on that type of locomotive operate at 300 pounds per square inch. The boilers are designed to withstand over 1,000 psi. So they're very rugged, very durable, very overbuilt. Well, that's important for several things, obviously safety, but the boiler is essentially the foundation of the locomotive. So most of what you're looking at on a steam locomotive is boiler. You've got the smoke box in the front, the cylindrical courses of the boiler, the combustion chamber, the firebox back where the cab is. That is all pressure vessel. When you strip it of all the jacketing, you can see how that big monstrous machine is held together. This is the front tube sheet. This is actually on the 844. You can see the superheater header up here. How many people know what a superheater is? A superheater is an innovation that they developed right around the beginning of World War I. What superheating does is it takes and it makes your steam more efficient by heating it up. So one of the big disadvantages to a steam locomotive is they're very inefficient. You heat up this water with this big giant water heater, if you will. This is not unlike most water heaters in your home. It's just laid horizontally, and the fire is on one end, and the hot gases of the fire flow through, and much of the generation occurs in the firebox itself. But a percentage of that heat transfer occurs as those gases, combustion gases, are flowing through these tubes and flues, and the smokestack is actually right above, right here. So all of that combustion gases, all that expensive fuel, you're only going to use maybe 8% of the heat. Right out the stack it goes. We can't get rid of steam locomotives quick enough. When the diesel locomotive was viable, the steam locomotives were gone. We don't like to hear that as enthusiasts, but that's the reality. So what the superheater does is it takes steam that comes out of the boiler from this header. If you can see it, we've got these little plastic cups in there to protect it. And the steam flows out and it goes through another set of pipes. We call them elements. And as they go through those elements, the gas from the fire is still really hot. So there's energy that you can derive, that you can still get out of that heat. So you heat the steam a second time. So the steam's 425 degrees when it comes out of a 300-pound boiler. By the time it's done coming out of the superheaters, you've pushed that temperature up towards 700 degrees. That's good, efficient. If you ever happen to be out when we're running the big boy, and we've come up a hill or we've been running fast for a while, and we stop, there's a crowd of people, and if you're anywhere near the front of that engine, you will be witness to superheated steam temperature. The front of that entire locomotive is 600 degrees. Think about that for a minute. That's the way it's designed. Stuff is smoking, the paint's peeling. There's no paint that can survive that. The paint peels right off. The oil is cooking, things are bubbling, you can hear it sizzling, and it takes about 20 minutes for that heat to slowly subside because of that massiveness of that locomotive. It's all hot. Rolling down the track with that thing, it's caught fire a few times. We've had some things back in behind, maybe a piece of newspaper inadvertently fell down in there, maybe some leaves we went through. It's a forest section and the leaves were just falling all over the engine. A couple of them worked their way down in there. Woof. And here we are, 40 miles an hour, and this flame coming out of the front of the locomotive. Nothing to see here. It's a superheated steam locomotive and something in there. We didn't intend for it to be there, but it's not there anymore. By the time we stop, it's going to be burned out anyway. So here we are inside the firebox on the work that we did. This is the 4014. This is where the heat is generated. This is where the fuel is burned. These locomotives originally were designed to burn coal. Let's talk about the cab forwards on the Southern Pacific. Anybody happen to know how many cab forwards the Southern Pacific had? How many? A lot.
24.
24? Anybody else?
40.
195. So the Union Pacific bought 25 big boys. And they were big, a 4884. They were huge. They were enormous. I don't ever want to invite a debate about which engine was stronger, which engine was bigger. We all know we have our favorites. The cab forwards were designed to burn oil, so their fireboxes were a little bit smaller. The drivers were smaller. The cylinders were actually bigger. The cylinders were the same dimension as the big boys are now. The big boys, when they were built, bear with me when I'm going to tell you all these statistics, but some of you know this, 23 3/4 inches. That sounds like somebody was crunching some numbers. Why not just round it up to 24? Or round it down to 20 whatever. It was very specifically designed. Well, those cab forwards were 24 by 32. Burning oil, let's jump back to that one real quick for me. And on an oil burning firebox, it doesn't need to be as big as a coal burning firebox. So when we converted the 4014 to burn oil, we didn't need all of that gray area. It's got 150 square feet. The cab forwards, if I'm remembering my numbers, were 139 square feet, 63-inch drivers. So if you look over here, you can see all these little pieces of metal. Those are called eyebrows, and there's thousands of them. Another little statistic here. Anybody want to guess how many staples in a big boy?
5,000? 4,050.
Very close. I heard 5,000, a little bit much. 4,449. Think about that. So here you are. Look at that. Look at the work that lies ahead of you. When you take a locomotive out of a park, whether it's the 4005 down in the 40 Museum right down the road here, or any locomotive, any steam locomotive, you've got that pressure vessel that was built back in the era that was built. The metal is old, the metal is rusted, the metal is fatigued. How in the world are you going to make this thing so we can run it again? Well, you get in there with a cutting torch. And anything that doesn't look like it's really solid, you get it cut out of there. And that's what we've done here. So this is called tube sheet. We fabricated that. Looks complicated, but it's not as complicated as you think. Then we cut out all of this metal. So the Union Pacific very generously, they were very gracious, and they gave them the 4014. They pulled it out of the line. It was in a line of engines that were gradually, they were cutting them up one after another. They were scrapping them, they were done with them. The metal was going to be melted down and repurposed. 4014 was the next one. They reach out with a switch engine. They bring it in the shop, they paint it up, they put new parts on it. Much to my pleasant surprise, a lot of new parts, a lot of the little ancillary things that go on a steam locomotive. Well, it goes out to the museum in 1961, several years before I was even born. There it goes, and it sits there for several years, and they were caring for the locomotive. But there was a small little leak in the smokestack, and the water came through there, and there was still a little bit of ash and debris in the firebox from when they used it last. Well, that water combined with the ash forms all kinds of things, and part of the stuff that's in water with coal, like your barbecue grill, sulfuric acid. And it slowly, over the decades, starts melting that steel down. Well, we get the thing back, and the guys at the museum were really worried about that. They were very apologetic. Well, I'm sorry, we didn't clean it out in time. Like, don't worry about it. You know what we're going to do? I'll give you the piece of metal that we cut out of there because that metal's gone. We're going to replace it with new. That's exactly what we've done. Back to my comment about these little pieces. Those are designed to help that metal survive the cyclone hurricane environment of the firebox. When that coal is being burned, a percentage of the coal never even lands on the fire. It flows through with such violent airflows and goes out the front of the locomotive and goes skyward. You see videos of steam locomotives, that smokestack is going up a long way. Well, that's air velocity. So you sandblast all of these pieces down. And there was a few locations where these, you can actually see that one is actually starting to wear down. And we tore our clothing up on some of them because they were really sharp. You know, they're just literally getting sandblasted down to nothing. Because you're producing 7,000 horsepower, the equivalent fire of 7,000 horsepower is burning in that locomotive. And inside of 4 hours, you're going to empty the tender of 28 tons of coal. And that 28 tons of coal is going to go through that auger. And that thing is blasting up. Remember I told you about 3-track and the modern locomotives today? Well, back in 1951, well, it would have been after 1953 when they built 3-track, that 4014 and all of its stablemates were doing the same thing. And they were blowing through 28 tons of coal. And there were some times when they had to stop at Harriman, which isn't that far from Cheyenne, and they had to take more coal or fill up with water. So how would you like to manage those logistics? So this is a really cool part of what we did. And we replaced, of those 4,449 stables, we replaced 800. When I first started discussing the rebuilding of the Big Boy, my intention was if we needed to, we would replace this entire structure in all 4,449 stables, if necessary.
What does the stable do?
What does the stable do? Well, the locomotive, it's a big, and that's actually a good picture. Let's jump back to that one. A stable holds the pressure surfaces of the inside heat transfer surface called a firebox plate. So you've got a cylinder, the cylindrical part of the boiler. So we're standing in the boiler right now, and I'm 74 and somewhat inches tall. And I can stand easily in the boiler and not touch the top of it. That's how big that thing is. Well, the steel itself, when it's rolled into a cylindrical plate, that structure is self-supporting. And you've got these big reinforcing plates called liners, and they're riveted here, and that's how the boiler is held together. When you get to the firebox end, that is no longer a cylindrical structure, it's rectangular. And there's some radiuses into that structure. Well, now you've got that 300 pounds of pressure is exerting 300 pounds per square inch. And if you do the calculation on the stable loading, you're like 7,400 pounds. I mean, this is a tremendous pressure that steam is exerting at all times. So that metal plate is held together with all those stables. Let's flip back just a couple and I'll illustrate what I mean. So what the stables, there's a good one. So you can see a lot of these little bumps here. Some of those are rivets. You can kind of follow the symmetrical lines and the rows of the liners. We're looking at the outside now. We were looking at the inside a few minutes ago. Now this is what it looks like on the outside. Notice there's nothing on these cylindrical portions other than where they're attached from one to the other. And you've got big reinforcing plates where you penetrate the structure, so there's a dome. We can actually climb down in for inspections and work on things. And the dome is also the highest part of the boiler where the steam is collected. But back to your question, so the stable's here. If you go to the 4005 at the Ford Museum or any steam locomotive, you're looking at the firebox, you see all those little protrusions. Those are stabled heads. And so the stable itself is threaded from one side to the other, and it secures that heat transfer surface. There's a lot of different varieties. I actually have around the corner a cart of, I usually bring a whole little cart of rusted stuff. And when we're done here, I'll get a few of those out and I'll show you what those are. These are the actual caps. So on the boiler, you've got this plate is 1.5 inches thick and thicker in some cases. And so all of the stay bolts are inside each one of these little caps that make it steam tight. And what they do is they have a little ball head, so it's flexible. So when the locomotive steams up in the morning, it's in a cooler state. As you heat it up, it begins to expand. And so those flexible bolts allow for a little bit of movement. If you didn't have that, the locomotive's so big, it would break so many stay bolts, it just wouldn't be economical. Lots of insulation here. You can just flip through.
Okay.
Now here we are on the inside, where I showed you that plate. I was talking about the superheaters. These are actually the superheater tubes, what we call boiler flues. And we're installing those, and you get to the point to where you run out of room. You know, when you put the first one in, it's just one little pipe laying on your side, and then you just gradually start putting more and more of them in. And each one of these, about 185 pounds. So it's a lot of physical work. Guys on the outside handling them. You wrap a little nylon strap around it, and you lift it and you pull it through. And the more you pull it through, the heavier it gets. It's really good exercise. I recommend it. This is a front tube sheet. So instead of a stay bolt, there's no room for a stay bolt up there. So there's another device called a tube sheet brace, and that's what these are. So the structure of the firebox is so heavy duty. Remember I told you that it's designed well over 1,000 PSI? Well, this is why, this is how. All of these giant braces, you can't quite see them the way the picture is taken here, but these are giant forged rods of varying lengths, and they all attach to what we call the unstayed surface. So any of this stuff here, above the area, the tubes themselves actually are attached in a way that holds one tube sheet and the other one together. Those are stayed, so that's a stayed surface. This area here, had it not been for these, would be unsupported, and there's no way it could withstand the pressure. So all of these structures here, when you're laying in there, they're all varying lengths, and some of them go all the way back to the dome, and they're all in a nice symmetrical radial pattern. And when you get in there and do the inspection with our annual FRA inspector, we take a little hammer in there, and we sound everything. We check the pins, we just check everything. Doom, 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 doom. And you'd be amazed. I'm a music lover, so I can actually tell the resonant tone. You know, you start down in the little short stay bolts, they get a little high pitch. Ding, 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 ding. You want to be really creative, take the wooden handle and go really fast. But well, here we are back in the front tube sheet again. This is how we connect all that stuff together. Well, look at the beautiful, shiny surfaces of the metal. And that's how you put that stuff together. So you clean up the tube, you clean up the hole, and the hole has to be a specific dimension. It can't be too big, can't be too small. And you have a special device called a tube roller, and that physically expands the metal of that tube. So all of the metal that we're using, a lot of people sometimes say, well, why don't we use stainless steel? Or why don't we use some high carbon, super space age, heat treated stuff? You know, it won't corrode, it'll last a long time in your boiler. But the problem is there's always a trade-off. And if you remember, I don't know if they teach this in school anymore, but you remember the expression, there's no free lunches? That's a steam locomotive for you. So we might be able to make stainless steel or nickel alloy or something that's going to survive in the corrosion environment of the water. But the problem is the heat's going to destroy it. So the trade-off is you use fairly low carbon materials, and these will rust, but all of that is something that you manage with the water treatment, which is a whole other world when you're talking about running a steam locomotive across a vast network of the Union Pacific, is water treatment. We haven't completely developed the system, but we're in the process of creating what's known as nanofiltration. So in the glass of water that you drink, or if you go to the store and you've got your favorite brand of bottled water, there's a proprietary blend of minerals that they put in there. I've read up on this. And you would think water's water, right? But it tastes different. And that's what you're tasting, is that proprietary blend of whatever they're putting in there. Pepsi has their own, Dasani, Coke, everybody has one. To me, it's just water. You pay $4 for a bottle of water, come on. Well, on a steam locomotive, I'll pay $4 for a bottle of water. So what the nanofiltration will allow us to do is take out all of the stuff that's normally in water. Some places you go and the water's good. You might even be able to drink it. Other places you go in the Midwest, when the water is living in thousands of feet of this permeated limestone, calcium, magnesium, all the stuff that's in water. Well, that dissolves. Water will dissolve that. And then you pull it out of the ground and you run it through your treatment plant and you drink it. Well, it still has that in there, and your shower head shows that. You know, what happens is that mineralization at the moment, it will precipitate out of the water. And what does it do? It sticks to your metal. It sticks to your shower head. It sticks to your pots and pans. Well, on a steam locomotive, that accumulation becomes a real problem from an economic standpoint, from an ability to transfer heat. Here you are with that 8% efficiency, and now on top of everything else you're dealing with, now there's calcium in the metal, and on top of the heat transfer services, that is slowing down that transfer of heat. You gotta get that out of there. So the solution is to not get it in there in the first place. And that's kind of what we're doing. So we'll be able to manage our water level wherever we go, wherever we travel to. We'll be able to sample the water right then and there, make a determination of what is the composition of that, how we want to soften it, and then filter it. And the resulting output of that will be a very specific spectrum, which we will deliver into the tender every day. Currently, we manage it through a process known as dilution. Very simple process. So as you're pumping the water into the locomotive, how many gallons a mile does a big boy consume? Anybody want to take a guess? Anybody been reading? Anybody been thinking about a steam locomotive?
300,000.
Through 300?
I know the tender carries 5,000 gallons of water, so
28,000. You're thinking of a K27, which is good. 5,000 is a lot. A K36, K28. So we've got 200 gallons every mile. So that big boy, just sitting there with the dynamos running, with the injectors maintaining the evaporative rate, the blower, the atomizer, all of that stuff, just sitting there, we're pushing 35, 40 gallons a minute, just sitting there. So the moment you light that engine up, your resources are being consumed, which is why they didn't play around when they left the roundhouse. When a steam locomotive left the roundhouse, they didn't stop at 7-Eleven. The 1940s 7-Eleven. They didn't stop over at this rich shack and play cards. And no. You left that roundhouse. You left the sand tower, the coal tower, the water tower, and you were gone. Because you're going to run out of fuel. You weren't going to make it. So here we are. We're burning we're evaporating 200 gallons of water a minute. Well, in that water is all of the stuff I've been talking about. Now we've got some chemicals in there to help us manage it. Those chemicals will react with some of the bad stuff in there and prevent it from sticking to the metal. We've got another really cool chemical reaction, diethyl hydroxylamine. What that does, it reacts with free oxygen. And it turns that free oxygen, by the time it's done through this really cool looking chemical calculation, it's acetic acid, which is a weak vinegar. So that takes care of the oxygen, so the oxygen won't hurt the metal. We take care of the scale, but what are we going to do with that cool proprietary stuff that they put in Dasani and all this other neat water stuff? That's still in there, because the engine is a really great distilled water maker. That water coming out of that stack, when you see that whistle blow, that's beautiful, pure water. And all the junk is left behind. Well, 200 gallons a mile times all the miles we run, that water's pretty dirty. So what we do is we let some of it out. It's called a blowdown. So when you see that 4014 running, you'll see this cloud just underneath the engineer's seat. And sometimes it's a big cloud. because we've got to manage those levels. So as we're looking at our chemicals, and we plot all this stuff on charts, and we leave Cheyenne, and here it goes. A few days out of Cheyenne, we're right where we want to be. Well, now what do? It'd be nice if we'd be there toward the end of the trip, but we're there a few days. We're up there. So we got to let that water out, we got to blow it down. By blowing it down, we hope, and again, it doesn't always work out that way, because you can't control the water that we're going to take at Rawlins, Sidney, Nebraska, North Platte. Pick a place. You can't control what that water is. Nor is it practical to try to have water ahead of you. Because when we talk to the people at Rawlins or Evanston or any place we go, we're going to take some water. They come out with this little garden hose looking thing. There you go. I'm like, no. We use 70,000 gallons. 70,000 gallons. And we can't sit here for 30 hours through your garden hose. So my trick is I call the fire department. Because when the fire department goes to respond to a fire, they're not using that little garden hose thing to fill their pumper truck. They're going right straight in. That's what we do. So that is a really fascinating part of the interesting journey as part of my career. I've got a friend who's a chemist. Many of you know him, Paul Tercio. He's a Notre Dame master's degree chemist. And so he's my peer review. I know just enough to make it sound like I know what I'm talking about. And I've studied and I've read and I know it. But I don't know it like he knows it. So I put him in charge of all these really cool chemical tests that we do. Because it's one thing to test your water, it's another thing to manage your water, but there's certain chemical and certain phenomenon that can occur within a high pressure steam boiler that are very damaging over the long term. Well, here we are back in. Remember those superheaters I told you about? That's what these are. And I think that people that developed the steam locomotives, how can I say this? What were they thinking? I mean, these things are complicated. And our world today, they're almost impossible. How many people work on a steam locomotive in here? How many people like it? It's hard work. It's very hard work. It's very hard work, and there's a lot of different opportunities to take a lot of shortcuts. And that was something I wanted to start talking about too. When you're working on a boiler, there's the way that they used to do it in the old days, when they would take certified materials, they were manufacturing them, they were available from a lot of different manufacturers. The railroads almost universally had some of the same identical processes and standards. There were differences from different railroads, but they weren't that significant. But the work that they did, the resulting quality, was necessary to maintain the longevity of the equipment. Just like today, the locomotive, we spend 2 or 3 million, on a big brand new steam locomotive. And the time that it spends in the shop is analyzed to the minute. That locomotive needs to turn around, it needs to get out, and it needs to make money. We're going to wear the wheels off of that thing as soon as we can. We'll put a new set of wheels on it. And that's the same thing with the steam locomotive. Well, the steam locomotive can't make you money if the superheaters are leaking, or if the staples are breaking, or if there's any number of hundreds and hundreds of defects on a locomotive. Well, when you go to rebuild one, you're looking for the right materials. Oftentimes, they're not as easy to select, they're not as easy to acquire. So you have to take the extra effort and require the manufacturer to give you certification. That's very common in industry. But the steam locomotive tests were a little bit different. So I was asking them to complete some of the tests that were considered to be obsolete. And they were replaced with other tests, or for whatever reason over the years, they just obsoleted. One test in particular is called a bin test. So you take this test specimen of a specific dimension and you fold it over on itself. So imagine a piece of Play-Doh, a cylindrical piece of Play-Doh, and you flop it over like a wet noodle. Well, you take a machine that has the capacity to take and flop that piece of steel over, and it has to pass that test with no deformation, no cracking, no breaking. Well, if it's the wrong specification of alloy, it's actually not an alloy. If it's got too much carbon in it or other elements, you will see through that test that it won't work. So we took a few emails and a few phone calls from me to get them to dig out their test and perform that bin test. The reason you do that is when you apply the staple, we're going to talk a little bit about the technical side of the staple. And would you mind for a minute, right around the corner, and my tote with the yellow lid, you'll see the big rusty staples. Your hands are going to get dirty. So he's going to grab one. I'm going to disappear behind the curtain for a minute. There's one there. Here, would you hold on to that for me? Grab this plate here. There we go. Oh, here we go. This is it right here. Okay. So this is a test specimen that we did. This is what's called a rigid stable right there. And I'll have it up here if you want to look at it when we're finished. And this plate represents that firebox plate I was mentioning to you. So this is the heat transfer surface. Inside here, where the microphone is where the heat of the fire is burned. And so the fuel is burning, and you've got direct flame coming in contact. You also have the tremendous heat energy, the light energy of the fire, which is tremendously powerful. You feel that. How many people shovel coal into a steam locomotive? When you open that fire door, what do you feel? You get a sunburn, and you wear sunglasses. The heat energy. Well, on this, that staple has to survive that. And that, I know it's difficult to see here, you can look at it here in a few minutes. That structure has to be low profile, and there can be no little edges protruding out of there because that fire is going to look for that, and that fire is going to destroy that metal. So you want the metal to be folded back into the heat transfer surface so the heat will dissipate through the metal. And you'd be amazed how quickly the heat runs through this and is transferred into the water. It's amazing physics, fascinating science of the steam locomotive. All very relevant in our coal-fired power plants, our nuclear reactors. It's the same principles, just done through much higher science. So when you form this bolt, it's kind of a little bit scraped up there because we held it in a vise. And we were wanting to develop the same tools and techniques that they used, so we're not reinventing the wheel. So we're going to have really good quality when it's all said and done. And we know that we've done our due diligence and we've put all 800 of those staples in there. So you can see over here on this one, this actually came out of the big boy. One of the first things we did is we drilled one of those out. We used a hole saw, we cut it out of here. And then we took it and we cut it in half. We could see what's called the telltale hole. And that telltale hole is exactly perfectly in the middle. And what that tells you, if this thing cracks and breaks, which can happen, the steam is going to work its way down through that crack. It's going to blow out the end right here in the center, and then you'll have to change the bolt out. So that's why we wanted to do the bin test, because we want to be able to do this by hand. You don't heat it up with a torch. Sometimes, if you look at the steam locomotive, those pictures we've been looking at and how complicated the thing is, your tendency is to find an easier way to do it. It's only natural. I mean, I'm open to any ideas, any suggestions. We've done 2 or 3 staples and we're exhausted. My shoulder hurts. I ripped my shoulder open. There's got to be an easier way. Well, there's not. So if you want an easier way, you're just going to have to leave the engine in the park or just run a diesel. But if you run a steam engine, this is the tough stuff you've got to do. There's another method, and if you turn that plate around there, so this method, that's not a welded bolt. I've got another one where you actually weld it in. And that's a newer process. Yeah, well, that's a seal weld. Yep. So you take this, when this is all done, over time, that tremendous heat, because that fire is 2,000 degrees. Steel melts at just under 2,400 degrees. So you're not that far from melting that metal. If there's no water behind this metal, you don't have much time. That metal will lose half of its strength at 700 degrees. So you can't let that metal get too hot. So what you do is you weld it together. And this is one of Jimmy's seal welds. So Jimmy did 800, and I think he did every single one of them. Look at that beautiful work. You're not seeing undercut. For those of you that know what a weld is, that's just absolutely excellent. So now what you've done is you've tied this metal through the weld into this metal. So now no heat can build up and eventually destroy that bolt. And we're talking over years and years and years. And this is going to last forever. I hope to live a long life. Hopefully I won't have to be, off in a, maybe, we all have places and care facilities, and my father's in one, it's a nice place. But when I think about the longevity of this locomotive, I naturally think about, well, how old will I be when they got to fix that? So that's in all seriousness, it's a legacy thing that I don't want to leave a mess for somebody else. I want to fix it. I want to fix this thing right. So this is a stay bolt on the outside of the boiler. So on the inside where there's fire, you got to do something very specific, and you want to use the right materials, want to use the right processes. Now this is on the outside, so you can walk up and look at this. So you do this by hand, and you can see these little striations there. That's probably, if I did this, it's probably my arm getting tired. But this is a hammer. You're actually using a pneumatic tool. And when you do the first one, you kill yourself and you wonder, I'm not going to be able to do this, and you're looking around and who's going to do this? All right, you do it, you do it. Well, you got to do some of them. Not everybody's going to be able to do every one of them. So you end up figuring out a little technique, and everybody has their own little unique trick. But the trick is to use the inertia of the tool and to use the power of the hammer and let that thing bounce a little bit. So you don't hold it all the way tight, you just kind of let it bounce a little bit. And you're watching this thing, and you're gripping it, and you're really, it's hard work, no way around it. But you're physically holding this thing, and it's louder than you know what. But you're letting that thing form, and pretty soon you get into this rhythm and this technique where you can do every one of them beautifully. And we each ground the tools a little bit different. Like my tools were different. You can see this might have been one of mine. And you radius the edge of it. And you hold it a certain way, and you form it, and hold it this way, hold it that way, and pretty soon you've got it all formed in there. Well, then you take another tool, and we each made our own little custom holders. I had some duct tape, some PVC tubes, and a wire. And I had my caulking tool in one, and my rivet tool in the other one, my forming tool. And I put the forming tool in there, and I pulled a caulking tool out, and it looks like a duck bill. And this is a hard part, because you've got to take that little duck bill, and you've got to shape the metal, and you've got to bend it into this metal, and just form it. Because if you don't do it, it's going to leak. And then when we've done all this work, months and months and months and months and months of work, then we're going to test it. We fill it full of hot water, and we start pressurizing it. We look for leaks. And one of the first things you do is you take a caulking hammer, you feel a little, sometimes it's a pretty big leak. Sometimes it's like squirting out like a spray bottle. Other times it's a little dewdrop. And you go back there and you caulk it up and you make it all nice again. 800 times. So Jimmy did a whole bunch of them. Austin did a whole bunch of them. I didn't do that many on this. I actually did. But I did a lot on the 844 when we did that work. This is a CAD drawing of parts that we make. So this is part of those boiler components. So we take the Union Pacific drawing a lot of times, and we just convert it into this three-dimensional drawing here. So that was the other fun part, is that we had all of the blueprints that we needed. Well, no exaggeration, I can probably talk for another hour. So why don't, if you're ready, we can take a few questions. I've got some parts here. We've got some more pictures I could refer to. This is the boiler shop with each phase of the work. So that part of the shop became the boiler shop. There was a period of time it was a superheater shop. It was the wheels shop. We had that whole giant shop of ours filled with whatever phase or whatever stage of work we were in. Chip Sherman.
Yeah. When are you going to release the schedule for your summer trip?
His question was, when are you going to release the schedule for the summer trips? I don't think that has much to do with boilers.
Well, we want to see the boiler work.
I know. Well, it's very soon. Yeah, we're ready. It's just, there's a lot of things that we do, a lot of vetting that we do, a lot of departments weigh in, and we're just managing all of that together. My piece of it is mostly done. My responsibility when they let us know where they want to go. So I project a 5-year trip plan for them to pick and choose from. And so I'll put together a trip out west, a trip to LA, for example, or a combination of all those things. So I'm saying it should be very soon.
Did you have to battle with dissimilar metals coming from varying manufacturers, parts, dissimilar metals?
What was the first part?
Did you have to contend with battle with dissimilar metals coming from different manufacturers?
Different manufacturers. The question was dealing with dissimilar metals. Well, most materials, they meet a certain quality specification, and that's a pretty narrow spectrum across the board. But we're really careful about when it comes to the boilerplate, that's SA 516 grade 70. It's a very refined grade of steel that's specific and it's rolled and it has a birth certificate, if you will, mill markings, and there's a chain of custody process that you're disciplined in managing all that stuff. We did run into a problem where we had material that was something it shouldn't have been. And the paperwork through a process of the manufacturer was defective, which is bad because they have to meet those engineering specifications, and it's very serious on their part on that type of breakdown. So what we started to do is we would do our own independent analysis. We'd take a sample of the material, we would send it to a separate lab. They run it through a spectrograph. They essentially burn the metal, and through that analysis can break down each percentage of the element and give you what the material is. And we found what was supposed to be 1008 was actually 1045. That may just be a number, but that's 1045 is like a bolt, like a good medium carbon bolt, a good solid bolt. 1008 is a very low carbon, stable, or rivet. And we did some work and the rivet head blew off. Well, that shouldn't happen. So anyway, that's how we discovered that. Good question. Yes, Matt from Australia.
Question on hydrostatic testing. Can you just talk through what you do for a hydrostatic test? Like what pressure and how long?
Well, in America, we're required in our locomotive, we run it to 375, so at 125% over its maximum allowable working pressure. So there's no time component with that. It's simply, we run it through that hydraulic pressure, we hold it at that pressure, the inspectors are with us, and we run through a series of evaluations, evaluating the critical structure, all of it. We're looking at everything from the superheaters, everything that we need to look at. The jacket is on it most of the time, when we're doing a 1472, which is our very thorough boiler survey, the jacket is off of it. So we hold it at 375, and I'm very proud to say that both the 844 and the 4014 hold their pressure beautifully. We actually have to vent the pressure to get it to come down. It sits up there. I've been around an engine, we couldn't get it up to pressure, it leaked so bad. The cylinder cocks look like a garden hose coming out of each one of them. There's water hemorrhaging out of this and hemorrhaging out of that, and that hydraulic pump can't keep up with it. We had to cancel the test. It was on the Challenger. The water just blowing out of the thing. So we had to regroup and tighten up a bunch of stuff. Not even one drip of water comes out of the cylinder cocks on the 4014. We've developed a process to handle the throttle on that. Because the throttle controls 7,000 horsepower of steam potential energy, power. It's got to be tight. So we service and we disassemble and reassemble that every single time. So there's no corrosion, there's no issues, and it is so tight. I mean, there's a few times it'll dribble and drip, and then, which is understandable. As long as you know where the leak is coming from, it's acceptable. But this last time we hydroed it, not even one single drip anywhere, other than like out of the blood. Did I answer your question, Matt?
Yes.
Right in front of it. Yeah.
I have a question about the Moffat Tunnel. Have you ever guys considered having like 844 or 4014 ever go on this Moffat Tunnel subdivision, or is it just not the right subdivision for?
So the Moffat Tunnel subdivision. Well, you're looking at a guy that's run a lot of trains on the Moffat Tunnel subdivision. Happens to be one of my favorite ones. This is where my seniority is. So the Moffat Tunnel sub is unique. There's a few curves up there that prohibit the 844 from running up there. So for those of you that remember or know anything about the Rio Grande, they had a class of locomotives called the M68. Remember what those were? Big 484s. Yep. Anybody remember what the driver diameter on those were? 70 inches. They were a big engine. And they ran them up there. There's a few 16-degree curves that still exist. Back in the steam days, there was a few more that still exist. But the M68 ran up there. I don't believe they derailed them, but they knew what that big engine was doing. So the 844, regrettably, is just can't handle the curvature. The big boy, on the other hand, can fit up there, but there's a few tight spots. Part of my responsibility is working with our clearance people, and you would be amazed and thoroughly impressed if you saw what they do anytime they run a train of dimensional clearances, a windmill blade train, for example, a big heavy transformer. Well, we don't need to run that stuff. We're the UP, we just run it up on the big railroad. That's what I call it, the big railroad. The transcontinental line that was built in 1869 that Edward H. Harriman perfected. It is one heck of an efficient railroad. I love the Moffat, but it pains me to see how little trains run on it. But there again, you don't need to run them on there. But to answer your question, don't quote me because I'm not officially saying we're going to do it. But if there is a need for us to do it, then that's my responsibility to get it there. And I've done a lot of homework. I've run the clearances on it, and it will fit. There's just a few places that are tight. Well, we got to do a little more homework on that. The other neat thing is that they've been running some passenger traffic over the line, and they want, there have been discussions about running other types of passenger equipment there, and it happens to be vertically taller. Well, back in the days when the Rio Grande was not part of the big major network it is today, that they kept the clearances and they maintained the clearances so they could run the 18.6 auto racks. They even ran those big giant 89-foot auto parts cars. So for those people who've got a long history in Colorado, maybe you remember that from the 70s and 80s. It was common to see that. The auto racks that we run today are too big. They're 20 foot 2 inches. They're just too big. But the big boy, it's tight. One of the things that we've done is that we measure everything. The years since 2019, we rushed and we got it out the door. And then we've kind of gone back and we've measured it. So I've had the people come out, my colleagues in Omaha, we have these laser instruments, and we analyze and we physically measure the locomotive. And from there we can project how much it will swing outward, how much it will swing inward, and where those areas. So every time that I take the locomotive somewhere, the step one is I reach out to my friends who handle all of our bridges and who handle all of our dimensions. And we have a process for that. It's called iClear. It's something all railroads use. So the very first thing, and they can give me, they usually send me an email back within 15 minutes giving me a thumbs up or a thumbs down. And they've all been thumbs up. There's just a few places the big boy won't fit. And the rest of it is a matter of just dotting the I's and dotting the T's. So long explanation, but did I answer your question? So you're looking at Mr. Moffat right here. If anybody wants to run the big boy in the Moffat. Okay, sir.
Yes, do you guys carry water purification with you? Is that how you deal with it?
This question was, do we carry water purification? The answer is yes. So we have inline filters, which are maybe a little bit more than a glorified swimming pool filtration system. So we're taking out chunks, big stuff. Then we run it through a water softening system. So that's an industrial version of what you'd have in your home, where you run it through that water softening resin bed. And how that works is kind of a neat. I'll just give you a real quick. It's a resin bead that's specifically designed, and it is not quite microscopic, but it's about the size of the head of a pin. And that thing is designed to attract the ions of sodium and calcium. So to get the system ready, you recharge it or you flush it with brine, with salt. So you take all the salt solution and you flush it through, you wash it. And those resin beads grab a hold of those sodium ions and they populate on those tiny little pinhead resin beads. Trillions and trillions of them. And you run that through, and now you've got this giant resin bed, this tank full of these beads ready to go. Now you pump your water through it. And that water goes through, and all the calcium in that water has a strong attraction, and it's going to take the place of that sodium. Now the calcium is going to get sucked out of the water. You like my sound effects? Yes. But the sodium is released into the water. So now you get sodium. And sodium carbonate, sodium bicarbonate. And that's what drives that pH up. And that's why we blow down so much. So to answer your question, yes.
So those are in your tool cars?
Those are in the tool car.
Oh, wow.
Now we're building a new tool car. It won't be online for a couple years. That new car is going to have mod 2, or actually mod 3, of my really cool water softening system. We're going to customize a really nice stainless steel vessel, because this is all like, it's experimental. We know it's going to work, but we're not going to invest too heavily until we're really ready to make the final commitment. And that's how we've just purchased this nanofiltration unit, which is, it's 20 feet long, a little bit shorter than me, and about 5 feet wide. And so it's a step below reverse osmosis. And so what nanofiltration is you're forcing the water under tremendously high pressure through a membrane. And the only thing that can fit through that membrane is a water molecule. All the other molecules and all the other junk can't fit through it. Well, where does it go? It goes into an effluent stream. So coming out of this nice, really cool car, it'll have a brand new generator in it. It'll have my steam plant, water filtration, water softening, and all kinds of other cool stuff. A chemical test lab, because right now we're kind of working on a little card table, doing our chemical tests. The tool car is jammed full of stuff. So we're just looking to create what's going to be the next evolutionary step of that process. But we need to do that. The cool story is that the company wants to run the big boy. When I say the company, I mean our corporation. This locomotive is for fun. Well, everything I've talked about is not really fun, but it's necessary. And therefore, if we're going to run the locomotive, it's got to be efficient. We have a budget. We stay within it. We have a plan. We work within that plan. And that's my responsibility, is to make this thing so it works. Because if we go the way we have for a lot of years, you're just kind of winging it in a lot of ways, and you're not really fully addressing the technical problems that are the Achilles heels of running a locomotive. It is a steam locomotive. There's one way to make it super efficient, and that's to put it on a park and to run a diesel. The other way to make it super efficient is to gut it and put a diesel engine or electric motor in there. Batteries. Oh, they'd love that. And then run it around. And a lot of people, yeah, we got a little smoke generator, and most people probably wouldn't know the difference. Well, maybe they'll do that, but hopefully they'll be long gone. I'm not saying they will. So anyway, okay, sir.
So, two questions. One, is there anything we can do to create a need to run the big boy up the mountain? Two, I follow some other organizations that are restoring steam engines that have been doing boiler work, one in Tennessee, one up in Alaska. They're nearing hydro testing on either of them. And I'm just curious, it's not a big world in the steam business here, right? How much information do y'all share back and forth with each other?
So question one is, can you generate a need for it to go up the Moffett? Let me come back to that one. The next one, do we share information?
Yeah, like consulting.
Consulting.
Because they're volunteer
Yeah.
organizations, you're not.
Well, there is a little bit of collaboration behind the scenes, but America is such an interesting country in that so many people are just fiercely independent, or maybe just independent. Organizations are independent. They kind of go it alone. You know, we know what we're doing, let's do it. Or, you know, and it's interesting being in the position that I'm in and having been involved with steam locomotives for years. I've kind of worked my way through organizations, and you see that. I'll just use the UK as an example. Again, maybe it's different, but from what I'm seeing from the outside looking in, you know, they have fundraising capabilities over there that really are fascinating to watch. And restoration projects that are off the ground and running and completed and running and successful. And then in America, it's a different dynamic. There's successful groups and there's successful operations, and then there's others that are just years and years of hard work and fundraising, and eventually they get the locomotive up and running. So I think it's just part of what makes us unique as Americans in our world. We just kind of do our own thing. When you take your car apart, you know, how many of you use the owner's manual? You know, I mean, it's just kind of what we do. So back to the Moffett, did that answer your question?
Yeah, pretty much. I mean, I'm
Yeah.
just wondering, like, technical knowledge.
Yeah, you know, the technical knowledge that we have is nothing secret. It's nothing special. You know, I've got a bunch of old books. Probably 90% of them are on Google. You know, much of what I have with the Flannery boat process, I got off of Google. You know, I got some old torn up book. You know, there's a lot of really cool books out here. You know, that's one of the things I do when I'm here. I go look for cool books. I got most of them. You know, they're very common. Airbrake books, boiler books. That one book that I had that was incomplete, I looked at Google Flannery Stables, printed out. There it is. I took it to Kinko's and made a bunch of binders out of them, and now everybody has one. And I've made, you know, again, it's not some super secret special collection that I have, but I have amassed through my friend Ed Gerlitz. He gave me his collection, and he had a vast library. And one of the things I did as the boss, the manager, I make sure all my guys have that. And I go to Kinko's and I have just print them out their own selection. So back to the Moffett. Can you create a need? Yeah, the best way to create a need is to write a letter. Letters are great. Emails are okay, but we all get emails. Usually go to the junk folder. It's another email. But a letter on a letterhead. A typed letter is great. A handwritten letter? No, somebody's probably going to read that. And I know that because they come to me eventually. Sometimes they come right to me, but a lot of times I encourage those who are interested to write our CEO. Find out who the board members are. Write them. Write the governor. Say, hey, Governor, can you say about the Union Pacific, blah, blah, blah. You know, those are the things that you'd be surprised at the impact they have. We all like to get an attaboy. We all like to get letters. One of the funnest parts is to get letters from kids. You know, you get this little handwritten letter or a picture. That's really special. So, well, how are we doing on time? Who's in charge here? Where did you go?
It's an open.
Oh, good.
It's an open.
Okay.
That's it, girl. It's correct.
Yep, that's Ed right there. Not the guy in the white hard hat. That's Ed. I had him come out. I said, you've got to come out. He was of the age where he was always giving me excuses. He called me Eddie. Hey, let's go to this. Oh, Eddie, it's going to rain today. Oh, and so we had a great relationship. He was my best friend, 30 years older than me, over 30 years older, but he's my best friend. And we got to a point of relationship, and I think you'll have that when you've got that age difference. You kind of start taking care of him. But I told him, said, we're moving. Well, he was the first person I told when we were going to restore Big Boy. I called him up and said, you're not going to believe this. Of course, he knew I wasn't pulling his leg. I pulled his leg about so many other things. But I told him, I said, throughout the process of getting it all ready to go, I said, you got to come out for this. We're going to move it out. We're going to move it a mile. So it was fun. Answer your question. Yes, sir.
You said you've got the boiler really tight under pressure.
Yeah.
Is it that tight when it's cold?
Invariably, it's going to leak a little bit cooler, but we don't ever test it cold. But it would probably be. And the reason you don't test it cold, part of the regulation requires that the water has to be warm. You know, you damage the metallurgy when it's cold. You know, unfortunately, I wasn't in charge, not that that's an excuse, but I've seen a boiler pumped with pretty cold water in it. Now, it didn't destroy it, but it's not good for it. Mr. Finch. His question was, when you say hot water in your hydro test, well, I'm only laughing because sometimes I don't really buy it. If a little is good, more is better. So if a little oil is good, maybe a lot of oil is better. Well, you're probably going to waste the oil. Well, if a little of temperature is good, wouldn't a lot be better? And I think in my mind it is. So if you're going to take that boiler, that big giant thing we've been looking at, and you're going to pressurize it, the regulation says that it has to be 70 degrees. All right, we're going to go 120 degrees. Oh, okay. It's uncomfortable if it splashes on you, but 120 degrees. That way we're closer to where this engine lives, because it lives at 425 degrees. Problem with that, you got to climb inside that thing the next day, and it's just been 120 degrees. And I remember our regulatory friends who are very thorough, and they are going to get in there with you. You're subjecting them to a sauna environment that is uncomfortable. So the request was, let's not make that so hot. No. Follow up, yes. Ah, yes. Where do we get the hot water? Well, we have quite the production facility there in Cheyenne. We have what we call a hot water plant, which is a big industrial hot seat. And we, like all of our machines, that's the neat story of rebuilding the Cheyenne steam program. We've gone through and systematically rebuilt everything. We got this machine wasn't used. The last time it was used, they just put it away wet, and now it's broken and rusted and it's junk. It's a $200,000 machine, it's junk now. All right, well, we got to spend $40,000 to fix it. So we've gone through and we fixed all that stuff up. Big industrial hot water plant. A steam plant, the steam plant was broken. So rather than use a steam plant, I got a smaller one and put it in a car. So now we have it with us, so if we need to. And on the second trip we run this year, we haven't released the schedule yet, but when we do, you'll see we're running 2 trips. And the second trip, we're going to be gone for so long, we got to do a boiler wash in the field. And while we do it, that's how I'll do it, with all this cool gear that we bring with us. So we've made pipes and heavy-duty steam lines that run up and run along and run down and connect here, connect there, connect this to that. It's really cool what we've done. Sir?
I have a video on the Reading 261, and it says that they have 7 throttle valves that they operate in sequence. Does the Big Boy have a configuration like that?
His question was the Reading, what number was that?
261, so 484.
Okay. Yeah, we have that like number. We've got a pilot valve and we got 7 big valves. I have one of them in my rusty bucket over here.
Why would they have so many valves?
It's called a multiple front-end throttle. And what each throttle does, it opens sequentially based on the flow of steam through that header I was showing you. And so the very first one to open is the pilot valve. So when you reach up and your hand is placed on this lever, that lever is controlling 7,000 horsepower. And you just bring it back ever so slightly, you unseat a small valve called a pilot valve, and that pilots steam pressure to the underside of the bottom of each valve called a balancing chamber. And so that steam helps to offset the tremendous steam pressure that's pushing each one of those throttles closed. So unless it's some type of mechanical failure, it fail-safes closed. And that steam can open. So the pilot valve opens first, then valve 7, then valve 6, till you have them all open. And we've done extensive testing and studying, and I'm a guy that needs to know how it works to the detail. So we open the throttle and we're up there looking at how much it's actually open, just so you get a sense of it. And you'd be surprised how little the lift actually is. To flow the equivalent of a 10-inch pipe blowing out of that boiler. 7,000 horsepower of steam screaming through there. So we have 7 as well. I've got one here if you want to look at it.
What caused the 3985 to get sidelined?
Pardon me?
What caused the 3985 to get sidelined?
What caused the 3985 to get sidelined? Well, it didn't. I guess technically you could say it was sidelined, but my plan was to completely rebuild that locomotive. That's the direction we were headed in. So I got what's known as an AFE, Authority for Expenditure. They gave me a very generous amount of money to rebuild the 3985. Right about that time, the conversation started from another party. Hey, I'd really like to see a Big Boy restored. Would you restore Big Boy? And then the question was presented to me, you want to restore a Big Boy? It wasn't, do you want to restore a Big Boy, or do you want to restore, it was, do you want to restore a Big Boy? And the answer was yes. And right after that was, well, which one do you want? Because we only have 2 engines. Well, it was clear, we're going to keep the 844. That was the last steam locomotive that the Union Pacific purchased. We're going to keep that one. Well, if you restore a Big Boy, most people, when they look at it, they can't tell the difference anyway. So if we would have restored the 3985, as cool as that would have been, to do everything we've done here, there's the throttle right there. Look at that beautiful forging. If we would have restored the 3985, the RailFan community would say, oh, that's great, they restored the 3985. It's cool. But when you restore 4,000, a locomotive is supposedly never going to be restored again, and et cetera, you've now opened an entire other realm of public relations opportunities that we still are benefiting from, because the 4014, people love it. They love the story of it. The world's largest locomotive, it's just part of a public relations piece that few people, I think, really were able to see at that time. So that's kind of how it all played out.
Was a mechanical parts failure another contributor to that?
Well, I wouldn't say it's a parts failure. It's just the locomotive had never been rebuilt thoroughly since it was in service back in the 40s and 50s. So you've got a locomotive that was run for decades with some maintenance done, but it's need to be completely rebuilt. And of course, as the locomotive continues to operate, each year more problems are presented and more workarounds and more temporary solutions to keep it running. And another temporary solution, the rubber hose, for example, the main reservoir, the brake pipe, all of that was a rubber hose from the front of the engine to the second engine, because all the pipes over the years were just rotted. And so just one thing after another after another. And a lot of the pictures that we have up there were all of the things, and that's how you get to where you are now. So we maintain the locomotive, we rebuild the locomotive, we use all those materials, and we make it so it's rock solid. So it doesn't get to that point, because if it does, the chances of it getting sidelined are very high. So keep the equipment as absolutely solid as you can, maintain it good, run it good, take good care of it, and it'll be around for years. Sir?
So on that point, kind of, So a couple weeks ago, I went to the steam shop tour that you guys hosted, and I learned that you guys, you're currently operating on a 6-man crew. How do you, as a leader, kind of manage this incredible amount of work that you have to do across these 2 locomotives, doing the snow blowing and whatnot? How do you make sure that everything gets prioritized, everything is held to that high standard while running with the few resources that you have?
Okay, his question was, how do we manage everything with 6 people? Well, most of the hard work is behind us in that we've rebuilt the 844. We took it completely apart. Now, let me back up. We didn't take it, we took the boiler completely apart. And we fixed those problems that it had. And then we rebuilt the big boy, literally from the ground up. So now we've got work that we need to do to maintain all of that. The rotary snowplow technically is not an active piece, and it's serviceable and it will run. So our task is to maintain everything. So we're in the process of installing some electrical safety equipment, some safety control systems. We'll do the same thing on the 844. And you go through your annual inspections. On a steam locomotive, it wears out most when you don't run it. If you let it sit around, and that was kind of the problem with the 844, and certainly with the Challenger, they would sit around with water in them, or sit around them wet and cold. And that wet and cold state, as you'll see on this bucket of parts here, destroys the metal. With our water treatment systems that we have, when the water is under pressure, you know, it doesn't have the same chemical properties that it does when it's just sitting there wet. That's really what damaged the 844 very significantly. Both tenders would have water in them year-round, 4 or 5 feet of water sitting in there. And you know, it's a steel tank, it's destroying the steel tank. Don't do that. You know, when you're done with the locomotive, bring it in, clean it up, thoroughly clean it out, thoroughly dry it out. And we've learned from those experiences of the past. So we'll keep an electric heater in there. So if you go at any time of the day, year-round, 24/7, 365, those boilers are very warm to the touch because that heat is driving out what little moisture could be there. Because remember, when the moisture is there, what does the moisture do in the world? What do lakes and streams do? They oxygenate. And so that corrosion is always happening. So you try to slow it down as much as you can. We have an extensive process of laying up the locomotive that takes about a week. Very, very labor intensive, but it is so thorough. Every detail is covered. Every valve, every moving part is thoroughly cleaned out. If it needs to be adjusted, we adjust it, we fix it. Then what we call lay up. And it's laid up with a solution. When we steam the engine up when we're ready to go, we have 1 day to steam the engine up. That's all we can afford. So it has to run as perfect as we can, and then we go. So we don't steam it up and tinker around with it for a week. We can't afford that because the regulation only gives us so many days to run. So that's how we do it.
You're talking about the 800 stay bolts, and I realize that when you need 800 stay bolts, you just call Alpha and they ship them out. How do you, this is probably a material that's not common. How do you acquire these?
He was talking about our stay bolts and our method of manufacture and our sourcing of equipment and materials. So we will source the specific grade of steel. We'll find a vendor that will do the test. I talked about the bin test. We'll double check it by running it through an independent lab to make sure it's the right stuff. And then we make them ourselves. And there's another place that we found that is a bolt manufacturer, so they can upset, which means heat up and shape. They can upset bolts and make bolts for us. They do a great job. We've had them upset and make some of the bolts, and then we'll machine them. So we'll machine the threads, and then there's part of the bolts here. They're what's called a reduced body. I didn't bring the really long ones, but I usually bring just a whole bunch of stuff. So what that means is that the center part of the bolt that's actually doing some of the work, is a smaller diameter than the part that fits in there. So the part that fits in there, and I have one right here actually. So when you look at this one, You can come up and look at it if you'd like. You can see that it's got